Okay, is that good day. Okay, welcome to the first online recording of 2101 Dynamics. Yeah, today we're going to talk about something known as polar coordinates. So, we're talking about two different methods of curvilinear motion, right? So we talk about path coordinates, we talk about Cartesian coordinates. So today we are advancing to one of the most abstract concepts available in dynamics, which is known as polar coordinates. And my main purpose here today was to try to tell you how the whole thing works, what's the purpose of polar coordinate, and how do we relate it back into motion modeling. So, the purpose of polar coordinate was to describe motion of particle, curvilinear motions, means motion including curvature and linear. So it's just like path coordinate and Cartesian coordinate, but it's a bit more complicated. So how do I explain the concept of polar coordinate? For example, let's say I have a particle here. Okay, this red color dot is a particle. And this particle is assumed to be moving vertically upwards along the y-axis perpendicular to the x-axis. So if today I were to model this motion of particle with polar coordinates, I will actually require two very different things. First thing I need is a rod. Just accept first before we go into the details what actually it is. So let's say we need a rod. Okay. This rod has one very interesting property. This rod has the capability to rotate 360 degrees above origin. And one thing to understand is that this rod is infinitely long. So we only draw finite on this, what is it called, this board itself. And the second most important thing we need is actually a ring. This ring can actually slide freely along the rod here. Okay, so you can slide freely along the rod. And we actually have what is it called, a rod that can rotate 360 degrees, and a ring that can slide freely along the rod. So, if today I want to model the motion of the particle, the idea of modeling the motion of a particle is basically tracing the particle. Makes sense, right? So, for example, let's say when the particle reaches here, this point here, I adjust my rod to this position and I slide my ring so that my ring coincides with the point. And subsequently, when time progresses, the particle moves to this position here. What happens is that in order to follow the motion of the particle, I also rotate this rod up to a certain angle, and then I subsequently slide the ring so that it coincides with the particle again. I think you've seen this thing. No idea why. Yes. So, if the particle reaches somewhere above here, I subsequently rotate the pole and shift my ring along the pole in order to reach this position. So what I've done, what I essentially done is that I basically managed to trace the motion of the particle by rotating the rod and shifting the ring, right? So in other words, if you were to look from a third-person perspective, absolute motion viewer, the motion of the particle is actually equal to the motion of the ring. The absolute motion, the absolute velocity of the ring is equal to the absolute motion of the particle. Does it make sense? Because the ring consistently follows the particle, right? So the motion of the ring is equal to the motion of the particle. So, and something interesting to note, first of all, the rod can only rotate 360 degrees above origin. The ring can only slide along the rod. So there's actually a geometrical relationship between the rod and the ring. In other words, in order to represent the absolute motion of the particle, I just need to know certain relationship between the angle of the rod, or angle information of the rod, and the sliding motion of the ring to calculate out the respective absolute motion of the particle. Get it? Is it clear for you all? So the first question was, how do I set up this equation? So, just a bit of an example. Assume that now my particle is at this position here. If my particle was now at this position, it means that I will adjust my rod to this position, and I will actually place my ring at this position here. So I need to have some kind of parameters to describe the rod and also describe the ring. So in this case, because the rod can only rotate 360 degrees, so some of the parameters that's important is, first of all, the angular displacement of the rod. Secondly, the angular velocity of the rod. And thirdly, the angular acceleration of the rod. These three quantities here describes the motion of the rod at that very particular position. In other words, describe the velocity, angular position, and angular acceleration of the rod at this position. Now, how about the ring? Now, first of all, we must understand one thing. We cannot know Because the absolute motion of the ring is actually the absolute motion of the particle, and it's actually our answer, what we want to find. Because we are concerned about the absolute motion of the particle. But however, we usually can find out certain properties of the ring with respect to the rod. So what we usually have is something known as R, where R is basically the distance of the ring to the origin. Distance, displacement distance, whatnot. Secondly is R dot. R dot is actually the relative velocity of the ring with respect to the rod. In other words, if you are the rod, or if you are super glued onto the rod, what is the velocity of the ring? That's R dot. Okay? And the third one is called R double. In other words, it's the relative acceleration of the ring with respect to the rod. Same again, if you were to super glue on the rod, what is the motion of the ring? So, if you think about this, if you were to stick yourself, this guy here, on the rod, what is the possible motion of the ring? It can only go two ways, right? The ring can either move away from you, or move towards you. So that's basically what I mean by R, R dot, and R double dot. So in other words, for R dot, R double dot, it's only basically the ring moving away from you, how fast does it move away from you, and the acceleration of it moving away from you, or towards you. When it moves away from you, it's positive. When it moves towards you, it's actually negative. So that's a convention that we are studying right now. For theta, theta dot, theta double dot, counterclockwise, positive, clockwise, negative, as usual. So, can the video record spot? Right. So, this is basically what we know about the quantities here. And if you were to look at the derivation that I provide with you on the WhatsApp group, you can see that we can correlate all these parameters into the displacement, velocity, and the acceleration of the particle itself. So assuming I want to find the displacement of this particle, means the displacement of the ring with respect to an xy axis, what I get is that the displacement of the ring, R, is equals to R direction theta. Right? Because this position, this point here, on the xy axis equals to angle of elevation theta plus distance of ring from origin out. So this is the displacement of the ring. The second part is actually called velocity. The velocity of the ring, the absolute velocity of the ring, is actually equals to R dot direction theta plus R theta dot direction theta plus negative. Okay, how do I achieve this particular equation here? It's just basically differentiating the first part. Just differentiating the first part. However, in terms of the what is it called, the method of derivation is basically posed on WhatsApp group, so you can just take a look yourself. I'm not going to focus on derivation because it's not very important. However, I'm going to explain what does it mean by these different quantities here. So this thing here, this R dot direction theta, is actually called as the relative velocity. And this R theta dot theta plus 90 degrees is actually equals to the entry velocity. So it's very important to know what is the difference between relative velocity and entry velocity. So first of all, we should remind ourselves that this V is the absolute motion of the ring, aka the absolute motion of the particle. Is equals to the summation of the relative velocity of the ring plus the entry velocity of the whole thing. So relative velocity basically means R dot. In other words, it means the velocity of this ring with respect to the rod. That is called the first part. The relative velocity is actually relative velocity of ring with respect to the rod. The second part is entry velocity. So what is entry velocity? Another term for entry velocity is actually velocity of the reference frame. And in this case, our reference frame is actually the rod. In other words, we are actually trying to describe the velocity of the reference frame using this entry velocity. And first of all, you must take note, this is actually a body, it's not a point. If it's a body, each point has a different velocity, right? This point here has 0 velocity, this point has a higher velocity. So when we talk about entry velocity, we are precisely, please pay attention here, we are precisely talking about this point which belongs to the rod but coincides with the position of the ring. Let me repeat, the entry velocity is the velocity of a point on the rod which coincides with the position of the ring at that very moment. If you look closely, the red color dot is not a particle, it's the red color dot is the point on the rod which coincides with the position of the ring. Since this red color dot is on the rod, it definitely is actually the entry velocity, and it definitely goes a circular motion, right? Because the rod can only rotate about the what is it called, origin. So in this case, the entry velocity is actually a circular motion which has a velocity in this direction. So this direction is basically equal to theta plus 90. If you look closely, is theta. This angle here is theta plus 90. That's why the entry velocity has an angle of theta plus 90. And the velocity of this this reference frame, in other words, the entry velocity, is equal to r, which is the distance of this point from the origin, as it rotates toward the origin, times the angular velocity of the rod. That's why this part here is known as r theta dot direction theta plus 90. Okay? That's all. So, let me recap, very important. This is one of the most important understanding. Relative velocity is velocity of the ring with respect to the rod. If you were to glue on the rod itself, what is the motion of the ring? That's called relative velocity. Entry velocity is velocity of the reference frame. In this case, our reference frame is actually the rod. Now, why is our reference frame the rod? Because our relative velocity is viewed from the rod. So rod is our reference frame, and the velocity of reference frame is precisely talking about the point at this rod which coincides with the ring, and it actually goes in a circular motion. And the magnitude of the circular motion is r dot theta dot, and the direction is theta plus 90. Okay, that's all. Any questions? Okay, now you guys get what I'm trying to say, right? Whatever. I'm going quite slow here. Yeah. So, and the third component is acceleration. Now, for acceleration, it's a bit more complicated. But let me write down first. So, it's basically r theta double dot, there's theta, plus, let's see, r theta dot, sorry. Oh, is it? R theta double dot, direction theta plus 90, plus, minus r theta double dot, theta dot square, direction theta, plus 2r dot theta dot. Okay, it's a bit awkward the position here. Let me just put this off and just put it somewhere here. So, acceleration. Acceleration is actually equals to r double dot direction theta plus r theta double dot direction theta plus 90 degrees minus r theta dot square direction theta plus 2r dot theta dot direction theta plus 90 degrees theta plus 90. Okay? So, what is this whole length of equation mean? What does it mean? So, as usual, we have the two components, which is known as the relative acceleration and the entry acceleration. So, this is the relative acceleration. The relative acceleration. Now, what is the relative acceleration? Same thing as the relative velocity. Relative acceleration is basically the acceleration of the ring with respect to the rod. In other words, if you were to glue on the rod, what is the acceleration of the ring away from you or towards you? That is called relative acceleration. And it's definitely pointing in the direction theta. Theta means pointing in this direction now. Okay? Now definitely if the ring is actually accelerating towards you, it's negative. It's accelerating away from you, then it's positive. It's always a convention there. Same thing here. If the ring is traveling away from you, r dot is positive. If ring is traveling towards you, in other words, traveling towards the origin, it's negative. Sorry, let me rephrase that. It's not away from you or towards you. If the ring is traveling away from the origin, it's positive. If the ring is traveling towards the origin, it's negative. If the ring is accelerating away from the origin, it's positive. If the ring is accelerating towards the origin, it's negative. Okay? Now, this part is the relative acceleration. Simple. Now, this component here, this whole component here, until this term here, is known as the entry acceleration. Now, if the entry velocity indicates the velocity of the reference frame of the point which occupies the same position as the ring, Same thing goes to the entrained acceleration. Entrained acceleration defines the acceleration of the point which coincides with the position of the ring. Now, first of all, as usual, this point here, red color point, the acceleration of this red color point denotes the entrained acceleration. And since the red color point is a point on the rod, and the rod is going 360 degrees around the origin, the point is definitely going in circular motion. And every single circular motion has two different accelerations, right? We have the centripetal acceleration. So acceleration ACC. And we have the tangential acceleration. So there's a reason why there's two terms why the entrained acceleration consists of two terms. Because the point that we say to undergoing entrained acceleration is this point on the rod, because it's the point on the reference frame. And this point is going in circular motion, and a circular motion always have two component acceleration. One is tangential, one is centripetal. Right? What is centripetal is r omega squared, is negative. So it's theta, so it's pointing towards origin, because it's a negative theta. And the tangential acceleration is pointing in this direction, so it's theta plus 90 degrees. Okay? Same again, if theta double dot is positive, it's counterclockwise. Theta double dot is negative, is clockwise. Same thing goes for theta dot. Now, the third one is the one that is most complicated. It's known as the Coriolis acceleration. Now, to be extremely truthful with you all, it's extremely hard to actually explain the understanding of Coriolis acceleration. If you want to go very deep, we can actually take a whole lesson to understand that, but I'm just going to try my very best to explain to you what does it mean by Coriolis acceleration. So, you can think of Coriolis acceleration is an acceleration that manifests in order to find the absolute acceleration of the ring. It sounds like bullshit, but actually it's not. So, just give me a moment, let me just prove it to you. Now, first of all, I think we can all agree so, on this first, we can all agree that acceleration term is formed by differentiating the velocity term, right? It's formed by differentiating the velocity term. So, the velocity term consists of relative velocity and the entrained velocity. So, in other words, if I differentiate velocity, I get acceleration. It also means that the differentiation of the relative velocity plus the differentiation of entrained velocity will also give me my acceleration. However, here's the interesting part. Okay? What is the differentiation of relative velocity? It's sort of like a change in relative velocity, right? However, you must understand one thing. Although the relative velocity changes, you must know, let's say when t equals to t1, the relative velocity is going in this direction, when t equals to t1. After a slight time, when t equals to delta t, for example, the velocity of the relative velocity becomes in this direction. These two directions is actually different. So we need an additional acceleration to change from this initial velocity to this velocity instead of just r double dot. And that velocity is always in a direction which is tangential to the rotation motion. That's why we have the first part, the Coriolis acceleration. The second part is basically entrained velocity. If we were to differentiate the entrained velocity, supposedly we will get the entrained acceleration. However, that's not the case. Because, and again, let's say, when we talk about entrained velocity, we are talking about a point which occupies the same position as the ring, right? However, you must know that when time changes, the distance of the ring from the origin also changes. So it means that the radius also changes, so it cannot treat it just like a circular motion. You need to have an additional acceleration to push it towards the exact acceleration here. That's why we have something called Coriolis acceleration. So, I know it's very abstract, but try to work out the way. So try to understand what I'm trying to say. So, in very, very simplistic term, Coriolis acceleration exists because A, the so-called radius of the entrained component is not constant, and B, the so-called relative acceleration changes direction. Abstract, but just, if you can't understand it, it's fine. Just try to understand that it's important to have a Coriolis acceleration. Okay, it's not that important. Honestly speaking, when I was doing this, I was also very confused on what choroidal acceleration is, but it's not that important. But you just know that it must exist. Okay, so how long have we got? 20 minutes. 20 minutes. Okay, so let's take a short break. Let's wait for one. Then after that, we'll go to the tutorial questions. Okay,